Hello, everyone. We are just waiting one more minute and then we will start the webinar, okay? Okay, so hello, be welcome to today's webinar, Mastering PID Control, the Art and Science of Tuning Cascade Controls. I'm Vera, I work in the marketing department of Control Station, and I will be hosting this webinar with Damien and Jack today. Thank you all for joining us. And before we start, I just want to say that you can anytime input your questions or comments on the control panel here in the GoToWebinar. There is a tab named questions. And in the end of the webinar, Jack and Damien will be answering some of these questions, okay? So our presenters are Damien Moreau and Jack Matthews. Damien has over 20 years of industrial experience, specializing in process control diagnostics and optimization with many manufacturers, and leveraging technical and engineering positions across key industries. And Jack is a president and CEO of Colorado-based TJ Labs. He has nearly 40 years of experience in process control and advanced manufacturing, having held engineering, RD, and managerial roles in the basic materials and chemical sectors. Jack received a degree in material science from the Ohio University. For those who are new to Control Station, we've been an active innovator since the 80s. Today, we are proud to support an increasingly global clientele, and our customers include leading manufacturing from across process industries. And TJ Labs, like Control Station, is an innovator. It's based in Colorado. TJ Labs is a full-service contract development and manufacturing organization. And the company core mission is to assist clients to bring quality products to market and efficiently and cost effectively.
Thanks, Vera. That's a lovely introduction. I just want to go through our agenda today. It's all about Cascade, but we're just going to kind of start at the beginning and work through some basics just to set the scene on why we are here, I suppose. You know, then we'll work through Cascade Control, the architecture, the reasons and benefits for it, and then a process by which we want to use to to be effective with that tuning, to be effective with the decision-making process, to come in, decide why, implement your Cascade Control and tune it effectively. At the end, we look at a case study. Jack has a lovely case study that we can walk through just to show other examples of it and we'll talk about the future of Cascade. It's been around for a long time, but there's innovation. Everybody's talking about AI and the potentials and opportunities that brings. Next slide, please, Vera. So we're going to share the survey question with you now, just to, I suppose, set the scene, give us an understanding of where you are with your Cascade Control. Obviously, you're here to learn. You want to get the information to become better tuning engineers, process engineers, and more effective use of Cascade. So please feel free to select one of those as to what you would most accurately describe your Cascade experience working with, etc. We'll give you a couple of minutes just to populate the questionnaire. As Vera said at the start, if you have any questions through any of the slides, please put them in the chat. We won't be commenting them at the start, but we will certainly go through them at the end to pick up the questions there and to respond to as many of them as we can with the time allotted.
Okay, so I will close and share the results.
Okay, so there's a good spectrum of, there's obviously a very strong one there, I suppose. Some experience, so 50% of our audience have some experience. That would be to be expected. But yes, I like to see that I have no experience. You're here to learn. I'm familiar with the concept, not used, but familiar with the concept. Again, hopefully you'll all pick up some nuggets of information from today and good practice, best practice, etc. Jack, what do you think of those results?
Well, I'm happy with them. Good morning, everyone. Thank you for having me. I'm happy with them because it looks like we have a lot of people who have the interest of learning, which is great. But I'm interested to see if we can maybe push the 24% where they're familiar with the concept, maybe push them into trying one. So let's see if we can do that by the end of the webinar.
Absolutely.
So good ideas here is kind of get everybody squared away on what cascade control is. Standard PID control, proportional, integral, and derivative is basically your regulatory loop. But I think today, Damien, what we're going to be talking about is how you could maybe use two controllers, an inside controller and an outside controller, as a way of supervising that regulatory control. And this might help us with something called disturbance rejection. We've all kind of hoped that we could track set points, but I think today's webinar, we're going to be talking about those things that happen far off in the plant that are going to impact your process.
Yeah, absolutely, Jack. The presumption is the PID has good set point control or reasonable set point control based on its tunings, but Cascade is all about that disturbance rejection. It's where we're going to dig into it. So next slide there, please, Vera. So just to kind of set the scene, we're going to use this shell and tube heat exchanger to be the kind of the talking point to talk through the reasons why Cascade should be implemented and the benefits and the considerations for it. We all know set point, controller output, process variable, but just looking at that graphic there, we see the two red arrows coming in from the top. That's a mixed feed of temperature coming in there, one from a warm liquid and one from a hot liquid. So there's a variability coming in there at the top. It's going to the shell and tube heat exchanger, which is being chilled or cooled from that left-hand line with the control valve on it. And then it's discharging out the bottom. We see the 140-degree temperature there. That's obviously our target temperature. That's our process variable, the one that we want to maintain. So that's going to give us that ability to control. Jack, we want to go to the next slide there. We'll take it up from there.
Yeah, I think that's next slide would be good. In this slide, I think what we're going to look at is the fact that we have two disturbances. If I look at this, the warm liquid and the hot liquid being mixed together, it looks like a valve, a manual valve up there on the warm liquid. Somebody could change that valve and disturb our process. So, okay, granted, that's a disturbance. I think that's the what we're going to call the warm liquid flow rate, then that you could be adjusting there. That is a disturbance. I'm not sure it's a good candidate today, but that is a disturbance. And then you've got disturbance number two. Looks like it's looks like pressure and flow from a shared header might be affecting the way in which that heat exchanger is cooled. So I think disturbance number two is the thing that we might be looking at today.
Yeah, absolutely. I suppose the disturbance two, that glycol flow and pressure, has a control valve on it. So the instrumentation or the equipment is there. The disturbance one has a manual valve on it. There would be a requirement to automate that if we were looking to reduce those disturbances. A very simple trick on that one, we tell operations to not radically change that valve if they need to adjust to schedule their changes progressively, I suppose. Next slide, please, Vera. Yes, training indeed. Yes, Jack. So the single loop process. So let's build on, you know, our desire to control the temperature on that system. We can see the PID block there is going to feed take the temperature on that exit temperature, bring it into the PID block, and feed that control valve from it. It's going to have that function there. We desire to maintain it at 140 degrees, and we're going to look at this disturbance 2, that's chill glycol. As the header pressure would change, the flow rate on that in feed of the chill glycol line would adjust with it as well. You know, so we're going to try and look to see, can we maintain that temperature using that control valve on flow. The complication there is if that disturbance changes, the valve will stay in the same position, but the coolability of that system will change radically based on the flow across that shell and tube heat exchanger. So really that's the issue we're trying to control, because if that flow changed, it would affect the coolability of the system, but that's going to take quite some time to get into the shell and tube, transfer across to the liquid and out to the instrument that's going to detect that change. So you're already in trouble. You're changing your temperature before we get to that. Jack?
Yeah, that's right. You know, the supply header there, that's, you know, perhaps common, right? You see this in a lot of plants where you have a common supply header, and different operations are going to be pulling on that that chilling liquid. Oh, okay, it's glycol. So chilling liquid is going to be glycol, and that's going to be a common problem. So this is in what we consider a single loop control, and it looks like that could be a candidate then to put the disturbance number 2 in some type of cascade. Next slide. So in our single loop control, we really want to maintain the effluent temperature from that heat exchanger. And that's the primary thing, and it remains the primary thing. So when we go to work on these disturbances, we never want to forget the fact that we're working on something that primarily has a control objective of maintaining a particular set point. So all we're going to do now is try to compensate for the fact that the supply header is going to be fluctuating, perhaps in its ability to carry away the calories across that heat exchanger. So disturbance number 1, whenever we have a disturbance or somebody moves that manual valve, for example, it's going to impact our temperature pretty quickly, and so that will cause the temperature PID to respond kind of in the same way, right? It'll act just like a single loop with that first disturbance. So we're not really affecting the disturbance number 1. Disturbance number 2, where we are going to modify our control set to take care of that change in the header pressure, that we could probably take care of with a secondary controller. And if you notice, they've got a secondary controller there. I can't see the number per se, but the one on the left-hand side is now the inside loop, if you will, the slave, and it's got a new instrument. It looks like we're going to measure, Damien, on the flow of the liquid going through that.
Yes, absolutely. And I suppose the location of the secondary controller, that inner controller, and the instrument relative to the valve that's going to affect that change. That's the key to cascade control, is that the instrument and the valve should be very close together, so you're quickly seeing the change and you're quickly responding to it. The migration from single loop to cascade is that change had to come all the way through our system and out the effluent outflow of that system before we started to see the change. But now we're sending a temperature requirement to a flow controller. So we're basically telling the flow controller, maintain me at 20 liters per minute to ensure I get the correct delta T across this heat exchanger. If the flow changes due to pressure variations, that inner controller, that slave controller, will respond much quicker to those flow variations and adjust to maintain that 20 liters. Next slide, please. You can see that on this next slide here, where we're just doing a comparison between those two different architectures, single loop on the left and Cascade on the right. And we can see there's 3 windows in each one: set point, change, disturbance 1, change, and disturbance 2. And looking at the single loop, we can see set point is, it's going to react and respond to a set point. Disturbance 1, the warm oil flow change, is obviously going to cause an upset. It's not a radical upset, it's probably less than 1 or 2 degrees. But you can see when the disturbance 2, the glycol header pressure changes, how radically it impacts. It's probably 5-7 degrees of temperature oscillation on our discharge temperature. And that's the one that's critical to us. That's the one that's making good product. That's the one that's ensuring that the downstream system is accepting that or receiving that 140 degree temperature. Comparing to the cascaded side, to that disturbance 2, similar on set point change and disturbance 1, but disturbance 2 is radically different. Now, it's radically different in that we're maintaining set point much better, quite obviously, but look at the work that it's doing with the inner trend. That inner trend now is the control valve's reaction. The valve is quickly addressing that flow change to make sure that it maintains that 20 liters on it. So it's going to rapidly respond to it. And that's the key to this, to cascade control, is that quick acting inner controller to recover or respond to those fast acting disturbances. The PID is tuned for temperature control, which is going to be slower on the process. It's going to have a different condition. Jack, you want to take it up from there on that?
Well, I just want to bear on the word better. It certainly is better, right, to running Cascade in this instance, where the glycol is going to change its flow. And I'm impressed with the fact that with Cascade control, you can often narrow the band of deviation that you would have if a disturbance was going to impact your process. And that disturbance rejection is what we call it in the control industry. That disturbance rejection is what Cascade is about. And this is a prime example of how to do it. Now, I understand maybe heat exchanger isn't the most key process, but in this case, it's feeding something downstream. And that could very well make a big difference in the quality of your product that you're making. So I want to just focus on the fact that the disturbance was rejected.
You make a good point there, Jack, about the heat exchanger. It's a single pass heat exchanger. You have one go to get that temperature correct. It's not like we can store it in the tank for a while. So if it comes out the discharge at 145 or 125, it's going to make the downstream process work hard. It's going to have to try and figure out what, and effectively we would be sending a disturbance down to the downstream system. That's so true.
Almost think of it like increasing our stability of that whole process. Next slide.
Stability factor is key, actually. You're dead right.
So if you look at the difference in trends here, this is what I was talking about with the single loop. You can see that the process variable is, moving around the set point, which is in light blue there. And they've got a 5-degree delta, if you will, around that, which in some cases would be fine, Damien. I think that in our case, though, what we're trying to demonstrate is that if we did run in cascade mode and a disturbance was going to try to knock us off a set point, cascade mode could allow us that little band of deviation around set point to be minimalized. And I think those fluctuations and trying to get those fluctuations as minimal as you can, I think greatly adds to the stability and the robustness of everything downstream of this heat exchanger. So I think it's a gallant effort to do that work.
Yeah, absolutely. So Jack, yourself and myself are of a similar vintage, where there was a degree of acceptance in variation in process. Modern manufacturing standards have gotten so much tighter. The expectation is much more effective control, no overshoots, rapid response, accurate response is what it is. So, getting the system to control to exactly where you want it is key. this, you know, quarter decay doesn't even happen anymore because you're not allowed to oscillate your process, you know. So it is what I would say.
That in a while.
So,
Yes.
yes, indeed. Yeah. So, but you can see in the cascaded loop, all the work has been done by that inner loop. It's you know, to ensure that the outer loop is maintained. We're selling the effluent discharge from that heat exchanger. That's the production requirement. We're not selling chilled water. Yeah, there's a degree of energy consumption on that side of it, and that's a different webinar, I suppose, about energy optimization. But you can see how much the inner loop is working to ensure those disturbances across the bottom are responded to and corrected to. You know, that's interesting. Just next slide there, please. I think we're jumping now to, oh, sorry, apologies, another slide here. This shows that clear benefits of cascade control, you know, that the disturbance is absorbed in that inner loop, the secondary, and the primary one doesn't see it. The last paragraph there sees the change and reacts to it. That inner loop needs to be reactive, I suppose. It doesn't have to be lightning speed, it doesn't have to be super fast, but it needs to be able to react quickly to those changes, to respond to them. You know, it's got to do with the process time constants of the two systems, which we'll talk a little bit further on. But you know, that it's making sure that inner loop can react quickly to those disturbances, so the outer loop doesn't see them, and the outer loop can maintain that set point management, maintain that 140 in normal process. Disturbances are in every system, but they're not normal. You know, if you have a disturbance in your process, you do need to figure it out. You know, Jack, as I said, I think it's something that people miss a lot of times, is that, well, I wanted to do both. I needed to do both, you know. What are your thoughts on that?
I think that's right. I remember what a French control engineer told me once. To do Cascade, you need a distant view. And I think moving that Cascade instrument far enough away from your process separates your process enough to where that inside loop has the time to respond and correct for that disturbance before it impacts your process in a major way. And I think that's the most important thing that we can think about, is that we do have now this instrument, but we want to move it far enough upstream, if you will, so that we can detect that disturbance before it really impacts our process. So I like the idea of seeing in distant view.
It is a good analogy for it. Good, sets the scene for you, very, very much so, yes.
Next slide. Oh, we have a survey question.
Again, let's just kind of, coming from the last question, I suppose, which of these are most appropriate to you? You know, as you know, Cascade is in lots of places, but is it everywhere, I suppose, is the question, or should it be implemented everywhere? Is perhaps the overriding question there. Take a bit of time just to have a think, but don't spend too long. Just, there's no such thing as a wrong answer, I suppose, there.
So if you think about your process and there's some opportunity for you to optimize disturbance rejection on one of them, and you think that's going to be a key parameter, you know, we call it key performance index. If you think about that, maybe there are, you know, reasons why you might want to look at one or two cascades for improvement, because it's attached to something that makes a lot of money, and that could be important.
Yeah, the word there is you know, is key process. Are we managing our control? And when we're not managing, is it just poor set point, or is it disturbances ago? You know, and again, you know, again, it's good to see the high number at no immediate plans. You're learning here to develop a strategy, but hopefully you'll go back and you'll start thinking about your loops and seeing where the disturbances are on it. You know, you know, Cascade isn't relevant in my plant's control needs, Jack. That's not. I suppose it's interesting, but not surprising, perhaps.
No, I
a
mean,
0%.
some processes are straightforward and single loop control would be fine, right? There are some things that are like that. But if you've got large mass that you're moving or a significant amount of product that you're extruding, for example, or you know, a lot of processing that's happening, you know, there could be a cascade situation that pops up. Maybe instead of thinking about the word cascade, we just think about what's knocking us off a set point. Is it something upstream that's knocking us off? Is it the weather? I mean, what is knocking us off the set point? And if it is a disturbance, then maybe we can start thinking about how disturbance might work. But there will certainly be times when cascade is not needed, and probably the majority amount of time, I would guess.
Yes, absolutely. I call it my why am I here question. When I'm standing in front of a loop, understanding we're very rarely standing in front of a loop that's performing perfectly. You know, we normally either are commissioning and starting one, or we're standing in front of it because it's not working. And you know, why am I here? Where's the disturbance coming from? What's causing that? Can I deal with the disturbance at source, or do I need to implement a control strategy like Cascade to respond to that? And is it worth that implementation, I suppose? Next slide, please.
Yeah.
Thanks, Vera.
The tuning method. Yes. Okay. So this is pretty handy. This method is called SIMPLE. It's just an acronym. It helps us to remember the concepts behind defining what your control objective is. I'm telling you, this is where a lot of money is made, is understanding where you're going to operate your set points, right? What normally are you going to operate in terms of all the inputs? You might even think about the normality, if I could use that word, Damien, without offense, of disturbances, right? What are the normal disturbances that maybe, if you've got a steam line, for example, you know, that could be a disturbance when some other unit operation pulls on your steam and you lose pressure. That's going to affect you in your process. So in this control objective, I like the idea that they use this moniker safety, right? Because you don't want to cause any problems from a safety standpoint. That's number one in our mind when we work on a process. The impact, I love that idea because, you know, does this loop fit in how does it fit in the overall process? Is it something like a surge tank up on a hill, or is it something where we're making money? Is it a continuously stirred tank reactor, for example? Okay, it might have more impact. Management, I remember that, you know, sometimes we don't do a lot of changes in process control just because we're trying to get more product out. So I have to be aware of that, you know, and that's kind of a much larger discussion. Profit, certainly. I'm not spending my time on loops that don't make us money. Longevity, yeah, if this loop constantly has a problem, or their operators constantly calling me to the control room saying this loop needs tuned, and I have to keep showing them that, well, no, really it's a disturbance that's knocking us off. You know, maybe I need a disturbance rejection there to help him and me, or her and me, to find a solution there. And then I think equipment, you know, equipment is expensive, and we want to make sure that we don't overpressurize a vessel, right, and damage it, cause that to go out of commission. A lot of these things are validated in my industry. We don't want to cause any damage, Damien.
Yes, absolutely. I suppose good control is simple, you know, and yes, we all know, though, they keep it simple. Acronym as well, you know, KISS, but it's something that we do have to think about as automation and process engineers, that when we implement these changes, we are going to affect that full range of safety all the way to longevity and equipment, you know, so you have to take those into account for that. And next slide, please, Vera. Without those considerations, then you do have to, you know, understand your process, understand the control loops that are there, and where are our problems. As I mentioned before, I call it my why am I here question. It's not the deep and meaningful one that sometimes you ask yourself. It's why am I standing in front of this loop? What's it not doing, and how do I implement a cascade on this? What will I need? You know, determining that master-slave relationship. The master is your product, the master is your production. The slave is the one that's going to do the work to ensure that your master is maintained. In our example, the slave was that inner flow loop. The master is that target temperature of 140 degrees. Implementing it, you could say, oh yeah, sure, we have an instrument there that's down the pipe, you know, but maybe it's too far away. Maybe it's not an appropriate instrument, you know, and all of those weaknesses in that location may require you to, whether we like it or not, put in a new spool piece with an instrument tap, or, you know, which is going to add to the, let's call it the complication of the project. Why not just use the instrument that was there, but it was, you know, 10 meters away, or, you know, it maybe wasn't a high quality instrument. So all of those have to be considered, because good information in means good decisions, means good actions on it, you know, so making sure that the instrumentation is right. Then that loop responsiveness, you know, is my inner loop going to be that fast actor? Have I the ability to make sure that it responds quickly? And we get this from the, not to delve into this, but the process time constant. What is the process time constant on the inner one versus the outer one, and how can we work those to our advantage, is what those implementation considerations. Jack,
I just remind everybody. Yeah, I just remind everybody that when we're talking about this loop responsiveness, it really is, you know, something like temperature is going to be a slower process than flow. Flow is very fast, maybe one of the fastest out there. So you want to be able to have your slave hopefully be something that's fast enough so you can detect it and squelch it before it impacts your process. And then your process has its own control for set point tracking. So there is a little game here that you play on this responsiveness characteristic for a loop. And so we do want the instrument to be far enough upstream that we get the detection, but then our response needs to be fast enough. We should not have a detuned controller. Detuned means it's very sluggish. I wouldn't have a very sluggish controller trying to capture disturbances and reject them. I'd have it tuned, you know, and hop it up a bit, you know, put a little bit of proportional in there and get the thing taken care of. So that the timing is important.
Indeed.
Slide. So in our 6-step, we're on step number 2, which is really the bump test. So what I learned from Control Station is that to understand your process, you really have to bump it. You have to be able to move that process around your control level, whatever, you know, your set point is that you're running. You have to bump around that. There are several different types of bumps here that they're showing you, but bumping the process shows or reveals the dynamic of your process. So when you do that, you can understand how then to tune your controller to regulate that set point. And so bumping the process is something that's very important if you're going to use some math to try to put your tuning parameters in there. Damien, for years, I started out just plunking numbers in there. I just opened up.
We're all guilty of that one, Jack. I think, you know, we've all done try a number and see what happens, and we get good at guesstimating or guess and testing. You know, is the thing. The step test is going to give you that usable information. First order plus dead time model, gain time constant to dead time. It's going to give you the numbers that understands how big that process moves, how fast that process moves, and how much delay before that process moves. From those 3 numbers, you can make very solid decisions on how you want to control it. You know, there's 3 different examples there. I like the doublet, and actually I like a double doublet. I like the repeatability of, if you look at each one of those changes, none of the steps have been repeated in the same direction. But if you do a double doublet, you get that repeatability. A PID is one set of tuning parameters using instrumentation and signals from it. If the process is not repeatable, you're going to struggle to get good control. So it's, you know, if you have a bad valve, a sticky valve, you know, variability in your process, you want to make sure that whenever you make a step up by 3%, and if you repeat that after a step down and step up again, that you get the same response is going to be very important. You can get some of this data from the step test, but you can also look at other pieces of information. Next slide, Vera, is going to look at that performance of the loop over time. It's again, I'm going to bring you back to my why am I here. Whenever I'm implementing these changes, I want to look for as much information from as much places as possible to understand, is my sensor repeatable? Is my valve repeatable? If I move it from 42 to 44% and back to 40 and back up to 44, does it settle out at the same point? Do we have a valve problem? Instrumentation, do we have noise on the signal? Have we a lot of chatter on those signals that are going to cause those problems? From your process data, you can look for oscillation and stability. Is the process oscillating? Is there a degree of variability in there that you're going to have to work with or against to compensate it? I suppose stability is that is my process stable? But you can also set up your tuning parameters so that they have an inherent stability. So if your process moves, that they're going to accept that and adapt to that. The guess and test method of tuning is something that isn't necessarily going to build that into it. It's back to the Ziegler-Nickel days when we just bring it to the teetering on the edge of oscillation and then just pull it back a little bit. But again, the process doesn't have to change too much before it goes unstable again, so it's something to and there is, systems and software. Our Loop Pro Tuner gives you those stability plots to be able to make those decisions on it. I want to go to the next slide there, Vera. So, Jack, go for it on this one. Apologies, I stood on your toes for this one.
No, you're fine. The thing I was going to add is that whenever you open up a tuning session, right, you're in the control room, you're going to go tune one of these processes, you often find that there's something else that you have to take care of. That's fine. I know it's an irritation, but that's fine because you're improving your overall process. So, don't not go into a tuning session, or don't avoid Cascade controls because you don't want to discover all the other work that might be needed. You might have to fill out some work orders, but that's all improving your process. So it's worthy of your time. This model is basically what they've done is they've got some cartoons here of a process. The left-hand side is what's considered self-regulating. This was an eye-opener for me too, Damien, because on the left-hand side, it's temperature, maybe pressure, maybe level, not level control, but maybe something like pH control. These all kind of responded to where you put enough of a titrant in there, and then you would come to some equilibrium chemically and in the process. And so a self-regulating loop is one that comes to some type of steady state. It reaches some adiabatic state. Temperatures are a great one in there, of course, and those all work like that. Flow is also another one that tends to, we pressurize the pipe to something and then we're done. But on the other hand, I learned that these pump tanks have this integrating process to them. They're not self-regulating. If you don't balance them out, I call it like a bank account. That's how I explain it to my people. So the bank account is, you got credits and you got debits, right? So in this tank here, it's got a pump on the bottom of it. And that means that we're going to have to balance this out. And anything that's got a balance point is probably going to be an integrating loop. Now, why do we care? The model, the mathematical model, we've come a long way, Damien. Now we're using models, right, to do this data work. And selecting the right model makes the big difference. You mentioned the first order plus dead time modeling. Yeah. Well, there's the non-integrating version of that, and there's an integrating version of that. And if you use the wrong model, you won't get the good tuning parameters out of it. So
yeah, my rule on all this is everything is self-regulating, level is non-self-regulating. It's the way I push it. So it's just the ready reckoner on that straight line. When I see that straight line of rate change, I go, uh-oh, this is a non-self-regulating loop, is what I do.
It reveals
There's
itself.
obviously a different mathematical version of it. It does, exactly. Yes, indeed. Yeah, okay. The next slide there, please. This one is, again, to focus back in on Cascade, you know, the efforts to set point track and disturbance reject, they're at opposite ends of the speed spectrum, I suppose, of a PID controller. And it's a mistake that we regularly fall into. We're trying to do everything with one set of parameters, and it's not always possible. You see 3 different plots on each one of these charts, a red, a dark gray, and a light gray. So those 3 different plots are reflective tunings for set point tracking and disturbance rejection. So the red on the set point tracking is the same as poor. So you have nice and stable set point trackings, nice and conservative control, you're going to have poor disturbance rejection. If you have very aggressive set point tracking, you're going to have aggressive disturbance rejection. You're never going to remove all of it, but you're going to certainly react much quicker. And balancing this is where the problem is, that people try and do it that single loop, and that they try and tune it to address that disturbance that only happens when the extra system comes on the chill water header loop that causes the pressure to drop. You know, if that's an infrequent event, you're tuning for an aggressive control. So always be cautious about trying to satisfy all of the needs with a single loop. Cascade allows you to be aggressive when you need to be and be conservative. Jack?
Well, I was going to note that somebody's made this graph and they've made the moderate tunings red. I don't think that means it's bad. I have a lot of things that are moderately tuned. I do understand that for those loops that are moderately tuned, disturbances probably aren't going to be captured as well as something more aggressively tuned. And so as a single loop. And so now that we have Cascade, I can have the best of both worlds. I can have my primary loop kind of tuned a little more moderate, if you will, maybe moderately aggressive, somewhere in there. But I can have my disturbance rejection loop, the inner loop, I can have it tuned pretty aggressive because I want it aggressive. I want it to go ahead and take care of my disturbance. And I think this kind of demonstrates how you can have different tuning variables to accomplish that objective. Next slide. And then here's where I think Control Station really shines, and that's where we have this modeling software that they use. You can model this other ways, of course, but I think their modeling tools are second to none. Really, when you do this step test and you collect the data, you can model it to one of the first order plus dead time models, either integrating or non-integrating. And when you look at this, it shows you a perfect snapshot of your process. Did the process variable overshoot? Well, in the first section of this, it did, right? And do I allow overshoot? In the old days, Damien, we had to, because that was part of our method. But nowadays, we're running so much product through the factories. We're just at the edge of capacity, or maybe over capacity, based on when the plant was built, that we don't want to overshoot. So maybe I want to tune this loop on the inside, the primary, so that I don't have overshoot. And that's basically what I would do. I would set that kind of moderately aggressive or moderate kind of tunings, and I would not have overshoot as demonstrated on the second bump. So
yeah, our software does certainly give you those two before and afters. You know, you do need to test it to confirm it's doing what you wanted to do, you're making sure that it's responding, it's reacting, but it's not oscillating and not overshooting. Indeed, but it's another mistake that's regularly done is we tune it, but we don't test it because we plugged it in. You do need to make sure that it's reacting the way you expect it to. It's another step test. Sometimes that step test can be generated from normal process operations, but typically you do need to exercise the process to move it away in the note down there. The PID only works on error. If there's no error, it's just going to sit there. You want to see it deal with change to understand that. And next slide. So the last part of this, again, is that of the 6th step is document, document, document. It only says it once there, but to record what you did, to show your change control, to show your colleagues, to remember yourself in a week, a month, or a year time when you have to come back to this loop because it stopped doing what it was doing. You know, to have a document that records the as found, as left, or as found recommended tunings, you know, the why it was done, who did it, when it was done, and you know what was the reason for it. You know, there's you know, take notes and take loads of notes. We've all lived with notebooks and taking notes in those, but we can be somewhat, I know I certainly can be somewhat inconsistent in recording the good details on that, you know, is the thing. Jack, are you a notebook guy? Are you
Well, we have both, of course. We have regular notebooks, but electronically on validated processes, we have to document everything, and the tuning is no different. Remember that we're controlling to some type of golden batch, if you will, where each pharmaceutical is manufactured in a certain way, and we can't allow deviations. And whenever we make changes to our documented to a validated process, we do have to document that. I love the report because I can also show other team members that here's what we found, here's how we took care of it, and it's a great tool in the production meeting as well.
Next slide there, Vera, please.
Next slide. Yeah. Oh, yeah. Okay. So here's something that I think is important. What we learned was that you probably are going to tune a cascade slightly different than you would a regular single loop control mode. Basically, what you want to do is use this in the right sequence. You just basically start with the inner loop, and then you want to have that basically in manual. You want to do your bump test. And then you'll tune that inner loop for a disturbance rejection. Why? Because it's the one that's seeing the instrument that detects that disturbance. So you'll set that for disturbance rejection. Typically, that's going to be a little more aggressive. And then you'll leave that one in automatic. Then you'll bump the outside loop, the primary. You'll bump it, leaving the inside loop as an integral part of the overall primary loop.
You actually basically set the outer loop as if it doesn't know the inner loop exists. You treat them as two separate PIDs, but the outer PID is quite obviously using the inner PID as its driver. You know, that disturbance rejection versus set point tracking. The inner loop is disturbance rejecting, is responding quickly, moderately, aggressively, whereas the outer loop doesn't need to react that aggressively for those disturbances anymore. So it can be set nice and calmly to maintain set point over a longer period of time. You know, and that's the function of it, I suppose, is that dual step test, I suppose, is what you want to do. You want to do the inner one and then the outer one. Next slide there, please, Vera. This follows on from that P to versus PI control. You know, if we think about the inner loop, we want that system to be reactive. Now, the best way for it to be reactive is P only control. Don't integrate that value over time. Don't you just do a reactive. So it's not always the best function, but as I said, you can set the inner loop to be reactive in responses, particularly if it's a slower loop. By setting it as a P controller only, it will react to every time that error. As soon as the error comes on, the P will respond to it. And you can over bias the proportional value to give it more push, I suppose. P control to everybody, again, it can build a degree of offset, a lack of accuracy of the control, but it will certainly give a responsiveness on the control. So that P only control can work quite well on that inner loop. We're not selling chilled water, so we just want responsive change in there. So if the inner loop is particularly slow, P control is an effective method of using it. Jack, I think we're coming on to your
Case study.
Your case study there now. So do you want to take control?
All right, sure. So this is a case study around a reactor. This is a continuously stirred tank reactor. It's disconnected at the moment in the picture, but I'm going to show you what it looks like when it's in place. Vera, if you want to go to the next slide. Essentially, this reactor is heated. We're basically building a buffer system that will support a couple of proteins that we're mixing. And so we have to bring the reactor up to temperature. And so we use a thermolator, trade word, heatilator is a trade name. But we use a thermolator then it's like a heat exchanger, but it's basically just a coil that runs inside. It goes through the top, actually. This is kind of a misnomer on the HMI, but it heats up the buffer liquids on the inside while we're adding the proteins, and then we'll titrate that with pH. So the overall goal here is to maintain temperature inside the reactor. It has to be at 37 degrees, body temperature has to be at 37 degrees Celsius. And so we'll use the thermolator then to raise the temperature of the reactor. Well, this is tank number 417. We also have tank 418 coming off the same thermolator. And so it can act like a disturbance because the two don't run at the same cycle. So I'm calling for heat, for example, out of this valve. You see there's a valve there coming out of the heatilator. I'm calling for heat through there, but tank 418 is taking that heat. So the thermolator is circulating around 45 degrees centigrade. And as it's doing that, if tank 418 pulls on it, pulls on that demand, if you will, the heatilator takes a moment to catch up, and that disturbs my process and can knock me off of temperature. So this process is validated plus or minus 2 degrees for the proteins to be considered good and not deactivated. So my primary objective is to maintain the temperature in the reactor as we're adding both titrants and proteins to it, and that is the primary loop, which you see kind of up there on the top. It's 4171 is the temperature control for the main reactor. And then 4172, if you can read that, it's kind of small, is the heatilator or thermolator's control system. So these are both temperature, Damien. Now what, right?
Temperature to temperature, yeah. And just I'm curious to see what the plots look like on this one now.
All right. So let's go to the next slide. There you go. So this is just basically a model that we built because Control Station now has modeling software that you can build your own, if you will. And this is basically showing that in Cascade mode versus single loop mode, the single loop mode thermolator does modulate quite a bit to try to maintain its temperature set point. Next slide. Just a model of the disturbance, if you will. And then this is the model of the process where we have the single loop, which is the yellow line there. You see it knocks us off a set point. I've superimposed the plus and minus 2 degrees bandwidth here for the temperature to show you that, we did ruin this batch by having this problem. And so once we put it in Cascade mode to reject that disturbance, we could see that the model predicted a very good outcome. So this is the advantage of doing modeling off-site, by the way. Next slide. So the upper slide there is the actual process variable. The blue one is essentially the primary process variable that I'm trying to protect. That's the reactor temperature. And then the yellow, and by the way, these are two different scenarios, Damien. So the first one is just running kind of normal, we're at temperature. And then the second half of that graph, I just smooshed them together. The second half of that graph is where the disturbance has already knocked us off. And so to demonstrate that we have disturbance rejection, the blue line at the top of that, the second hour, if you will, that I captured, shows that we did have an impact from the disturbance, but my primary loop controller is also responding. So it is bringing me back to set point, and I didn't exceed my threshold.
See, it's a factor 2.5 smaller, you know, with that the cascade control on it, disturbance rejection. It stayed inside your 2 degrees, I suppose, but it stayed inside your 2 degrees compared to the previous. The yellow is 5 degrees plus, you know, so that's significant.
Well, in this case, yeah, it's a good batch versus a bad batch, if you will. Now I've got to, you know, involve quality, and we've got to go find out if we've ruined the proteins, and many ELISA tests later, we find out the result. That's a lot of money. So we implemented Cascade control to take care of that problem. And the Cascade is simply the thermolator is just detecting temperature upstream of the reactor, and we're just offsetting that and circulating more. It's a lower temperature fluid that's coming through there, but we're doing more of it to continue the delta T in the reactor. And you can see
from the 2 lower plots. Yes, sorry, go ahead.
I was going to say, in the lower plots, you can see that there is some change. The middle plot there is the control valve, and the green is the inside loop, and the red was the outside loop. Yes, there's a little bit of oscillation here. I understand that. We probably could do a little bit better job of that, but there is some oscillation comes from my upstream from my thermolator. But it's a very low amount of oscillation.
Like the oscillations of 0.5 or something on that lower trend, you know. Yes, indeed. Yeah,
and the bottom is the actual glycol temperature control, and you can see it does oscillate a bit. I probably could improve that, but overall, it does a much better job.
So,
it is modulating the set point. Do you see that, Damien?
Yes,
the set point at the bottom is modulating with the ebb and flow of that thermolator's temperature.
The other benefit of Cascade is that it shows you the other process variants that are in there, like that oscillation. That some of those oscillations wouldn't be evident under when the disturbances are being hit so hard, because it's forcing the system to work. It's only when you actually get to calm down a system by using Cascade can you then take it to the next level and improve the set point tracking, or the outer loop control, or the more critical parameter, to give you that more stable control.
That's a money maker for us.
Yes, absolutely. And you know, those bioreactors are very temperature sensitive. They really don't like the variants on it. Just to round out the discussion, the next slide there, Vera, is, you know, so what's next in Cascade control? You know, it's been around for a long time. PIDs themselves have been around for, I dare I say, a century or more. And you could go back to P controllers that are hundreds and thousands of years old. But you know, in our manufacturing industries, they're certainly around the guts of a century, and they haven't changed that much in those times. You know, we're all talking about AI and smart sensors and APC and MPC and all these things. They're still using the fundamental PID block in the core. You know, there is innovation occurring around getting the information to the controller more effectively, cleanly, with smart sensors, cleaner signals, better data quality. All of those things are in that middle group there, which are going to feed into those 2 outer, advanced control. You know, can we make better decisions by switching the values we're using, switching the tuning parameters? It's one of, you know, advanced APC control is going to change the tuning parameters, but gain scheduling has been around forever. As long as the PID exists, it's very underused. You know, so advanced control using gain scheduling is adapt your tunings as to where your operation can be very effective on that. Within Cascade, it's adapting your control when your disturbance happens, you know, and work it faster or slower in that. AI process needs models. And so to be able to read the process and generate the model on the fly is going to need more instrumentation, more data. It's going to look for that more data. Jack, where are you on the AI function
Well,
within PID?
you know, from one standpoint, writing letters to my customers, it's great. From the other standpoint, I can tell you right now, Damien, we're not going to let ChatGPT run around the plant. That's not going to happen ever.
No,
Okay.
indeed,
However, I am anxious to see what you guys are going to come up with, because diagnostically, I think this is a game changer. But it's
very much
diagnostics. I don't think we're going to let the basics of our control. We have validated processes. I'm not going to revalidate those processes just because AI showed up. You know, we are making good product today, so I don't see that having an impact.
Certainly steps towards that. You know, we're getting much better data coming back from the instruments and the valves now. We can make better decisions on the health of the valve, on the health of the instrument, to start saying we need to change here because there's a problem. But again, you're right. ChatGPT, or even it's the next generations. There's manufacturing is slow to change those kind of things. They're certainly coming, and they exist out in the data analytics side, but they will migrate across that firewall into the DMZ at some point, I suppose, you know. But as I said, it'll be done very steadily and softly, I suppose, but not at a great pace is what I would expect. We certainly have looked at a few, and we're looking to integrate that data into our monitoring product, Plant ESP. That certainly gives us that ability to look at performance over time and detect those. So there is certainly functions there on it. Vera, I think we have another questionnaire at this stage. We're right on the time, so good and bad. But just finish out with a questionnaire. But while you're answering the question, Vera, can you see if there are any questions there that we need to?
There is lots of questions actually, Damien. So we are going to address some of these questions here in the webinar, and the others we will address by email. We will contact you because
right on the time. We are talkers. Apologies for that.
So this is the last pool, and then we can move forward to the questions.
Do you want to give us one of the questions? Just conscious of time, people are going to start going to another meeting or whatever. But
okay, so how is the disturbance determined and considered to be an issue? Is there threshold values for it to be considered?
It's a good question. We talked about speed. Sorry, Jack, do you want to go? Do you want to take it?
No, I think you'll be fine, Damien. I'm just going to add to the fact, yes, determining what a disturbance is and what its impact is. For us, I can just tell you that anything that's knocking us off of the set point that is not related directly to the tuning of our single loop controller or some other process that's happening, you know, that other process that's happening might be the culprit. So yeah,
yeah. What I would say is your processes, everybody that's in this call, you have disturbances in your process. You don't see most of them because they're happening slower than your PID tunings are set up for. You only see the disturbances that are faster than your PID tunings. You know, and so that they're the ones that start to hurt you. And so looking at your process time constant of your process and looking for disturbances that happen quicker than that are the thing. If it's a factor of, you know, 0.2, 0.5 faster, your PID will attempt to recover some of that, but it may not be able to do it all. I would expect after 0.2 or 0.5 of a time difference between the two process time constants, is then process time constant to disturbance time constant, then you're going to start to see the error increase, and that'll drive that. Are we hitting the 1 degree over set point, the 1 degree oscillation, which will drive that decision on it, I suppose. Hopefully that answers your question. It depends on how much faster your disturbance is. There will be another question.
Yeah, next question is, are the PID gains identical for both inner or the outer controllers, the same or tuned differently?
Go, Jack. Yeah.
Well, no, I think that's one of the reasons why I like modeling, right? The model will tell you basically what the response is to that inside loop versus the outside loop. So that's very helpful to model them with a first order plus dead time model. The other thing that you're looking at is that you have two different control objectives. Your inside loop, we're hoping, is going to reject this disturbance quickly so it doesn't impact your main process. Therefore, you're probably going to do something aggressive. What does that mean? Probably a higher value in the P term. And now, if you're using proportional band, of course, it's a smaller value. But if you're not using proportional band, your KC, for example, probably would be more aggressive on the inside loop than it is in the outside loop. The outside loop is you're going to get it tuned to track the set point as best as possible, and it's going to be probably a little more moderate to moderate aggressive. What do you think, Damien?
Yeah, absolutely. You know, I've seen, like Jack, in your example of your reactor, I've seen temperature controllers on those kind of systems, and they have equivalent or similar time constants. You know, so they're going to react kind of at the same speed. You do need to push that inner one to work harder, and the only way to do that is increase the proportional term. It doesn't mean that you can't control them if their time constants are similar. You just need to have to work that inner one harder is the thing, I suppose. So indeed. One more question maybe, Vera?
Yeah, maybe one more question. And as I said, we will address all the questions by email after the sessions, okay? Yeah. So main tank level is controlled by the discharge pump, but other pump fits into the main tank, disturbing the main tank level control. Can main tank control be configured to ignore the frequent disturbance feed coming from another pump? It's a hard one.
It is a hard one. So
you want me
to have
again?
No, I think I have the concept. So the tank is being discharged at a rate out of this by a pump, but there's an in-feed pump controlling it. What you would need to do is cascade the level control of the discharge pump to the in-feed on the other pump, so that, you know, based on the demand in the tank, you could do it. Now, the one proviso I'd say on all of this is level control is probably one of the most misunderstood and miscontrolled processes out there. We should ask the question, why was the tank put there in the first place? It most likely is a buffer to allow those variabilities in flow, perhaps. So I would think, you know, the level in that tank, does it affect the quality of the material in that tank? And if it does, there are certain scenarios that it does affect the quality of the delivery out of that tank, but not out of a pumped tank, I would say. So it is possible to maintain accurate level using that kind of a system, so that you're wanting to maintain a level with the discharge, but you're going to use the in-feed to ensure it speeds up or slows down based on demand. You know, so there's a potential that to maintain level based on that pump feed in. But I would argue, I know of 1 or 2 instances in industry where level is critical to the product quality. You know, carbonated delivery of liquid into bottles and cans is one of them, because they're gravity fed, you know, and level is going to feed that. But there aren't too many others that the quality of the product is needs to have a 50% level in the tank, you know, is the thing. So hopefully that kind of gives you some perspective who's asked the question. Follow up with us by all means. You can see our names there. We're readily available. I think we've done enough at this stage. Thank you for everybody that's coming. Anybody and that's still here. You can see all the lovely faces of our sales managers from around the world. Hopefully you'll be engaged and interested in learning more about Cascade, learning more about the training that we can offer on PID control. And the whole training program does include a full, almost 2 hours, 3 hours perhaps, of Cascade control in it, worked examples, scenarios that you can use. So if you want to learn more, please reach out to look for more details on our PPC training. Look at our website for PPC training and you'll get the information. Jack, thanks for the conversation. It's been useful. And any comments there?
No, I think I would just want to thank everybody for their time and send questions in. We'll help them answer.
Yeah, you can see our webinar that's coming up next in April. So please feel free to look out for it, look at for it on our website, and you'll be able to register for it. They're well attended. We had a rock star number for this class, you know, so appreciate you all and sticking around for it as well. So until next time.
Thank you all.
Tuning.
It was great.
Thank you all.